Hello, am I audible? Hello. Yeah, thank you for the confirmation. So we'll start the lecture in 1 or 2 minutes. If other people join, it will be good. I'll say this video is recorded and uploaded on the YouTube as well, and you can watch the lecture if you miss it now. I guess we can start now. Other people will join. If anyone missed, they can watch the YouTube session. So welcome everyone for this deep learning course, IIT Ropar. I'm Abhishek Thakur, Primary Research Fellow at IIT Hyderabad. So this is the week 7th of the live tutorial session of this course. So every week we discuss the some of the important question based on the lecture session of that week. So we will also discuss today the question based on the week 7, which is already uploaded on the NPTEL portal. So let me just confirm whether this video is recording. Yeah, it's recording. So today we will see some of the important question and also it will clear the basics of the week 7 lecture. And if you have not seen the week 7 lecture, then if you see this tutorial session, then it will be little easy because some of the basics will be covered in this. Or you can see the first week 7 lecture and you see the tutorial session. Then this tutorial session will be very easy for you. Okay, because both are almost similar. So we'll start with the first question that is based on the bias and variance. So in this question, it is given that there is a model fx hat to predict the value of y. Uh, the mean squared error is given as y minus expectation of y minus f hat x squared. So this is given as bias squared plus variance plus sigma squared. So now in this question, it is asking about the comment on the bias and variance for a good model. So you can also answer if you know this answer in the chat box or in the YouTube comment box. But before that, we will see some of the basic concepts related to bias and variance. So here, let's suppose there are around 10 points in our data sets like this. So there is like two kinds of model. Like if our model is very complex, like it is of high degree, then it will in the training data set it will perform very good and it will cover all the data points, okay, for very complex model. This blue curve is for complex model, okay. And let's suppose we have a very plain model like this, and why this black curve is here, black line, because the mean squared error from the black curve is minimum as when you calculate for each of the points in the data set. So this is of like degree 1 and this may be of higher value degree, because we can write this line as y is equal to wx plus b, and this is some polynomial curve, okay, of degree greater than 1, maybe 3, 4, 5, whatever. So now you can see clearly here. So this is our simple model in this curve, and this blue curve is our complex model, and the red curve, that is our actual value, that is the true value, okay. So now we can see here that for simple model, it has a very high bias, and for complex model, it has a very low bias. Actually, bias is defined as, I will first write what is bias. Bias of f hat x is equal to expectation of, okay, like this is the expectation of the predicted value minus true value. So here you can see the difference between the expected and true value is too high in this case. In the simple model case, the difference between the expected value, sorry, my video is off. The difference between the expected value and the true value is very high. And when you see in this complex model case, the difference is very low. Okay. So it is clear that the simple model has very high bias and the complex model has very low bias. Okay. So this point is clear. Now we will see in terms of variance. So I will just repeat, just to summarize whatever we talked. Like in this, we can see that simple model has very high bias as compared to the complex model, which has very low bias. And bias formula is given using this. That is the difference between the expected value of the estimated value minus the true value. So here you can see there is a large gap and low gap in the like complex model. So now we will see for variance. Variance is given as variance of estimated value fx hat is given as expectation of, yeah, this is true. So variance of fx hat is given as expectation of estimated value minus the true value square. Okay. So now here you can see in the simple model, when there is some variance, like when some data points are changed in the simple model, the variance are very low. You can see all these curves are for simple model. Variance are very low. But in this, you can see in the complex model, for some changes in the data points, variance are very high. So it is clear that simple model has low variance, whereas complex model has a high variance. So now we'll solve the first question based on these concepts. So comment on the bias and variance for a good model. So the good model should have trade-off between the bias and variance. Okay, like it should have low bias and low variance as well, but it cannot be possible with like simple model alone to give both the low bias and low variance, or by complex model only to give the low bias and low variance. So here the option A is low bias and high variance. This is a wrong option because we don't require high variance. Option B is high bias and low variance. Here also we don't require high bias. So these two are the wrong option. Low bias and low variance. So if we will have low bias and low variance, uh, like I have to discuss this also. Here you can see this is the error versus model complexity curve. So here you can see when the model complexity increases, the error is reduces. Okay. Here you can see when model complexity increases, error reduces. Okay. And but Like when error goes to zero, at this time you can see the variance is very high. So we are interested in not these points, that so that we will increase the model complexity to the infinite level to get the error zero. We are, in this case, our model will not perform good with the test data set, but it will give zero error with the training data set. So it is the case of overfitting. So we are interested in this point. This is the perfect trade-off between the bias and variance. Here, this is our ideal model. In this case, the training, it will give low error in test data set all as well, and in the training data set all. So this is also not possible. High bias and high variance is a very bad case. So the correct option is the optimal values for both bias and variance. Okay. So if you have any doubt, then you can ask in the chat box in this first question. Or when the video is recorded and uploaded on YouTube, you can also ask in the YouTube comment box. There also I will reply. Okay. So now we will move on to the next question. That is based on the error and model complexity. So in this question, there is four statements are given and we have to find which statements are true. Identify the correct statements on the general trend exhibited by training and validation error with model complexity. So the first option is validation error decreases to zero by increasing the model complexity. So this is wrong because when we increase the model complexity, validation error does not decreases to zero. Only the training error decreases to zero. Validation error may increase when we increase our complexity of the model. The statement 2 is training error can be driven to zero by increasing the model complexity. So this is correct. As we can see in this curve, training error can be brought to zero after increasing the model complexity. Now option 3, that is validation error decreases up to certain model complexity, after which due to overfitting, the error starts increasing. Yeah, option 3 is also correct. Here you can see this is the curve of validation error, and this blue curve is for the training error. So in this curve, what we can see that this validation error first decreases up to the certain level of model complexity, and after that it increases. Okay. So from this point, it started increasing. So option 3 is the correct. Option 4, training error decreases up to certain model complexity, after which due to overfitting, the error start increasing. This is wrong because training error keep on decreasing up to zero. So which are the correct option? That is option 2 and 3. That is given in option D. So anyone have any doubt in this? If not, then we can move on to the next question. That is based on the error and model complexity. So here, given a model to identify animal, dogs and cats in an image, like most of the models are based on this, which identify either it is a dog or it is a cat in the given image. So which point is the right choice? So at which point our model is very ideal, that is the right choice. So at point A, it is a very simple model because the model complexity is very low. So in simple model, what will be this point A exhibit? That is high bias and low variance. Okay. And this is the complex model because model complexity is increased a lot. So at point B, it will be low bias but high variance. We have already seen this in the previous curves. And point C is the ideal point. Here the model is perfect. There is trade-off between bias and variance. Okay. So any doubt in this? So the correct option is A point is wrong because it have a very high bias. At point B, that is also wrong because it have a very high variance. Point C is optimal and that is correct, and both A and B, that is also wrong. Any doubt in this question? Like why we are taking both bias and variance into the consideration? Because you see, this mean squared error, this depends on bias and variance. So what we have to do, we have to make a trade-off between bias and variance to decrease the mean square error. We have to make trade-off between bias and variance to reduce the mean squared error. So now we will move on to the next question. If you have any doubt, you can ask in the chat box. So coming to the question fourth, that is state true or false in the context of a complex model. More sensitive to changes in observation, and second, omega theta would be high. Okay. So we will see in the complex model, like simple, and this is the graph you can see down here, that is given for the simple and complex model for some given data. This is given. This is our simple model, which is the straight curve, and this the curve, which is like sinusoidal, is our complex model. So let's suppose after changing one of these data point, just one data point is changed here. You can see. After that, what happened? The simple model does not change. Okay, as compared to the complex model, you can see the changes in the complex model is more. The changes in the complex model is more as compared to the simple model after changing one of these data point. Okay, so it is more sensitive to changes in observation. So the this statement one is correct. Okay, because complex model are more sensitive for changes. Okay, and this omega theta would be high for the complex model as compared to the simple model. So both one and two statements are true. Okay, like we know that our loss function is written as This is the formula for loss function with respect to theta. So here this omega theta will be high for complex model. So both options are true. Any doubt in this question? So next we'll move on to the fifth question, that is based on the overfitting. Given a deep learning model, identify the technique you can adopt to reduce overfitting. So we have to reduce overfitting. So what we can do, we will increase the number of data on which our model is getting training. Also, we can do that using data augmentation. So data augmentation is a process of artificially increasing the amount of data by generating new data points from existing data. So how this data augmentation is done? In data augmentation, we can generate more number of data by rotation, okay, translation, or scaling. We can do these, we can perform these operations, and we can increase the number of data, more number of data in this data augmentation, so that model is will get training for different kinds of data, and it will work better with the test data. So it act as a regularizer also, as you have seen the proof in the class, like in the lecture of week 7. It act as a regularizer and helps reduce overfitting when training a machine learning model. Okay, I'll just erase this because it is also just like a noise. So data augmentation is the correct option. And also, if we collect more data, then our model will have like susceptibility for the more number of data. So it will work well with the test data set. So collecting more data is also very good to reduce overfitting. The next is perform regularization. Uh, After performing regularization, you can see it is a set of techniques that can prevent overfitting in neural networks and thus improve the accuracy of deep learning. Okay, how this when it facing the completely new data, then the regularization will just reduce the error and it will just improve the accuracy of our deep learning model. So regularization is also one of the technique which can be used to avoid overfitting. Next is reduce model complexity. We know that when our model is more complex, then it will work better with the training data set, but it will give more error with the test data set. So we can reduce the model complexity, but there should be some trade-off between bias and variance to keep the error minimum, and accordingly we have to keep the model complexity. We should not reduce it to completely a very low complex model. That will also give high bias. So option D is also correct. So all of these options are correct for this question. Okay. So now we will see the next question. If you have any doubt, you can ask in the chat box, or you can comment on the YouTube if you see the lecture after this class. Next is data augmentation. Question based on data augmentation. Which of the following is true for data augmentation? Better learning in image classification and object recognition. Yeah, that is true. Second is possible for any data. No, it's not true, because let's suppose we have like some defects in a machine, and if we just rotate or do some changes for data augmentation, what will happen? The position where defect is there in the machine, that position will change. So in this case, it is not possible for all the data. Okay, point B is clear. Now the point C, it does not need domain knowledge to generate more data. It requires a domain knowledge, like because it works well in image classification and object recognition things. Because if we rotate cat and all, then also the image of cat will be like same only because we have to just classify whether it is a cat or dog. Okay, or even like this is 2 in the MNIST data set. Let's suppose we have rotated. So this is like very poor. So this also can be rotated so that it can detect such kind of things also as 2. So it requires the domain knowledge. Okay, it requires the domain knowledge. So option B and option C are wrong. Option A is correct, and all of the above cannot happen. So option A is the correct option for this question. Okay. So now we will move on to the next question. If you have any doubt, then you can ask here. So coming to the next question, that is based on the early stopping. So you are training a neural network model using early stopping technique. Given that patience parameter is 3, that is p is equal to 3. So when will you stop the training? So this is our epochs. This is training loss. This is validation loss, and this patience parameter is given. So when we will stop this? When we will stop this training? Okay, so just you can answer this in the chat box. So okay, in this question, as we all know that when our validation loss, that is validation error, is either being constant or increasing in the last in the last p patience parameter, like last in last p epoch, that is patience parameter p, then we will stop the training. So just write the point. When validation error being constant or increasing in last p parameter, in last p epoch, then we will stop the training process. Okay, so now we will check when we will stop, at which epoch number we will stop. So here you can see in epoch 1, the training loss is 2.1 and validation loss is 2.0. Okay, so let's draw the curve only, that will be better. Number of epochs. Red curve is our training loss. Let's check another color, that is green color. Green is our validation. Okay, so this is our number of epoch is 1, 2, 3, 4, 5, 6. And this is our 1.6, 1.7, 1.8, 1.9, or let's take little down. Take 1.6, 1.7, 1.8, 1.9, 2.0, 2.1. So first we will plot the training loss. So, but we don't have to see the training loss while determining our early stop parameter, that is patience parameter. So anyway, we plot. So on the epoch 1, this is our training loss 2.1. On the epoch 2, this is on epoch 3, 1.9. And after that on epoch 4, 1.8. So this is our training loss. Okay. Now moving on to the validation loss on epoch 1, that is 2.0. After that 1.9. After that again 1.9 in epoch 3, and in epoch 4 also it is 1.9. In 5 also 1.9, and in 6 it is again increasing, that is 2.0. So this is our epoch 6, it is 2.0. So this is the curve for the validation. Now we will see, like if the continuously for three epoch, if the loss is either constant or increasing, then we should stop our training process. So here you can see, this is the first time the loss is constant, second and third. So P is equal to 3. So we will stop here. This is our stopping point. Okay. We will stop the training process here. Because for the continuous three epoch, for the continuous three epoch, the loss is either constant or increasing. So what is this epoch number? That is epoch number 5th. Okay. So the correct option is option C, that after epoch 5 we will stop our training. Okay. If you have any doubt, then you can ask. Let's say we will move on to the next question. This question is based on dropout. In dropout, what we do, we just drop out some of the neurons from our model, and so that the other neurons will be actively participating and updating the weights and other parameters. And the weights and parameters are updated when that are active and which is related to that neuron for the subsequent like for in dropout we are removing some of the neurons. So for the in some of the model, some weights parameters are not there. In some other model, some weight parameters are not there. So what we do in the models in which weight parameter is existing, it will get update in subsequent models. So given that there are 25 nodes in a neural network model, what is the total possible thinned networks that can be performed? So the total possible thin networks can be performed is 2 to the power 25. So option B is the correct option. Okay. Like I will just show you. This is our input layer. This is our hidden layer. And let's suppose this is our output layer. The figure is getting cumbersome. So it's okay, leave. So this is our, each are connected from each other. Okay. Now, what we will do, we will just remove some of the neurons. Let's suppose we have delete this. We'll delete this. And now our model will look like this. Okay. So this is one of the possible thinned layer. So if there are 25 neurons, then there are 2 to the power 25 possible thin layer. Okay. So dropout, what it does, it applies a masking noise to the hidden units and it prevents hidden units from co-adapting because the other neurons are very active, so it does not adapt from the other neurons because it thinks that maybe other neurons are not active, so they will actively participate. Okay, essentially a hidden unit cannot rely too much on other unit as they may get dropped out anytime. So in this case what happens, these neurons will not depend on this neuron most of the time because they know that any of the neuron may get dropped at any time. So this neuron will be very active while firing. Okay, and each hidden unit has to be learned to be more robust to this dropouts. So the 2 points to be noted here. The point one, that is a hidden unit cannot rely cannot rely too much on other units. Why? As they may get dropped at any time. And each hidden unit has to learn to be more robust to this random. Each hidden units has to learn to be more robust to this random dropouts. So these 2 points are very important. This question is very simple, but we are discussing the basics of dropout technique. Okay, and this dropout technique can be used to reduce the overfitting. So in the process of training deep neural network, you achieve 100% training accuracy and 35% test accuracy. How can you reduce this? So in this case, you can see that training accuracy is equal to 100% and test accuracy equal to 35%. Okay. So here you can see this is the case of overfitting because model is working good with training data set and it is failing on the test data set. So case of overfitting. So this can be reduced using dropout techniques. Okay. So dropout techniques, what does it do? It ensure the redundancy and the robustness. Okay. And it also just reduce the uh, overfitting case. So now we have done with all those questions. This is question number 10. This is last question. This is based on noise. Okay. So in this question, what it is given that so that the adding noise to the input is equivalent to the L2 norm regularization. So we have to show that when we add some noise into the input, it works as a L2 regularization, and this can reduce the overfitting as well. So we will just, this is just a proof kind of question. So let's suppose the noise is given as random variable with zero mean and the variance is sigma square. Okay. So such kind of noise is standard normal noise. And let's suppose our input is xi, but after adding noise in input, xi tilde that is equal to xi plus ei. Okay. And we know that estimated value that is y hat that is given as I is equal to 1 to n wi xi. But this is the estimated value. Now next is our x is added with some noise. So in this case y tilde will be I is equal to 1 to n wi xi tilde. Why? Because xi tilde is equal to xi plus ei. So in this case noise is added in this input. And so it will reflect in output y as well. Okay. So this will be given as I is equal to 1 to n wi xi, because xi tilde is xi plus ei, summation I is equal to 1 to n wi ei. This is our y tilde. So y tilde, this term you know, this term is y hat. When there is no noise added in the input, the estimated value that is y hat. So y tilde is equal to y hat plus summation of I is equal to 1 to n. Any problem up to this equation? If you have any doubt, then you can ask in the chat box or in the comment section. So now, in what uh, in what term we are interested? We are interested in mean square value. So we have to find mean square error value. We have to find this term. Okay, this is equal to expectation of y tilde. What is that? That is y hat plus summation of I is equal to 1 to n wi minus y whole square. So now what we will do, we will write expectation of, we will just club these two terms, y hat minus y plus I is equal to 1 to n wi ei, and we will do this square. Okay, this is our mean square error. Up to here it is fine. So now we will write it as this term, we will take it out, plus 2 into expectation of y hat minus y summation I is equal to 1 to n wi ei. Done. And the third term will be expectation of I is equal to 1 to n wiei square. Okay. So these are the three terms. This is the first term, second term, and third term. So we will just see the second term first here. Let's erase this. So this will be expectation of y hat minus y into expectation of wiei. Why? Because ei is independent of everything. Ei is independent of y hat minus y, and also ei is independent of like wi. So this and wi is just a simple weight, so it will come out, so it will become like this. Expectation of, keep it inside only. See, these are like wiei, so we can write this term as summation of I is equal to 1 to n, expectation of this, into expectation of I is equal to 1 to n ei, because this ei and wi are independent, and we know that this term is equal to 0. So our second term is equal to 0. So this will become expectation of y tilde minus y square, that is equal to this first term, that is expectation of y hat minus y whole square, plus, sorry, plus this third term. Third term, what is that? That is expectation of uh, wiei squared. Okay. So in this case, it will become expectation of I is equal to n ei squared into expectation of I is equal to 1 to n wi squared. So we can write it as the mean square error loss as this term is the variance of noise. So that will become sigma squared into summation of I is equal to 1 to n wi squared. So this you can see, this is same as L2 non-penalty. So we conclude that adding noise to the input is equivalent to the N2 non-regularization. Hence, adding noise to the input is equivalent to L2 non-regularization. So today we will end the lecture here only. And if you have any doubt, then you can ask in the chat box, or you can ask when you this lecture will be uploaded on YouTube as well. So you can ask in the YouTube comment box as well. So I will reply there also. And today we will just close the lecture here, and we will meet after the week 8th lecture, that is on 17th September. Thank you everyone for attending next lecture. Thanks everyone. So we'll close this lecture now. We'll meet on 17th September, that is week 8. Okay, bye bye. Thank you.